In this video, we're going to be talking about the simplest ARIMA models, barring the seasonal component. So these are called non-seasonal ARIMA models. The first part of ARIMA models is the AR component, which is the autoregressive models, which is derived from the word auto, which is saying regressed on itself. Auto meaning self. And so what you see here is that if you have a time series y, this is just regressed on the past values of itself. Okay, so you are regressing yt, so y at time t is regressed on yt minus 1, yt minus 2, and so on and so forth. What you have here is a constant term and also a shock or innovation at time t. Okay, and it is assumed that this epsilon is a white noise process. So for the purposes of notation, what you are going to have is a regression that is going to have a lag order of p, and therefore if there are p lags in your regression, the AR model is going to be represented as AR of order p. So in case you're just regressing yt on yt minus 1, that would be an AR1 model, and we call that an autoregressive process of order 1. So P is determining the lag order or the number of regressors that are the past values of Y itself. So here you have a representation of an AR1 process, an AR2 process, and of course these graphs are going to vary a lot based on the values of phi, which is really controlling the degree of persistence that is there in the data. So here's a process that you can simulate. You may not get things exactly like this, but very similar to this. If you have a process which is autoregressive of order 1 with the persistence parameter phi being very high at around 0.8. Okay, and this is for a time series of length 100. So you can construct this. This is something we did in class. Now, for an AR1 model, we want to remember that in its simplest form, this is how it can be written: yt equals some constant plus phi1 times yt minus 1 plus epsilon t, where epsilon t is white noise. So whenever phi1 is 0, that means if the persistence parameter is 0, the time series is just equivalent to a white noise process, right? So you would just have yt equals c plus epsilon t, and that's a white noise process. When phi1 equals 1, that means if your persistence is 1 and the constant term is 0, this is equivalent to a random walk, which is sometimes heavily used for financial time series. When phi1 is equal to 1 and the constant term is not equal to 0, this model is equivalent to a random walk with drift. Okay, so there is a drift term that would shift the series up or down. And when phi1 is less than 0, which is mostly what you find in different time series, then you have a case where your time series tends to oscillate between positive and negative values. Okay, so here is an example of an AR2 model where you have different values of phi. One value of phi is 1.3 and the other value is negative 0.7. And you can see the way the AR2 process looks like. So you might sometimes think, well, this looks like a white noise process, sort of roughly horizontal with maybe some peaks here and here, but really it's not. You can actually exploit the data to model it and figure out or get closer to the data generating process. Now there are many restrictions that are already programmed into any software you're dealing with for time series that ensure that the autoregressive models are restricted to stationary data, and that involves just constraining some of the parameters that are estimated. So general conditions for stationarity would mean that the complex roots of your characteristic equation lie outside the unit circle, and this translates into some restrictions for different types of autoregressive models. For example, the absolute value of phi 1 is going to be less than 1, which is displayed right here. And then there are different restrictions for AR2 models. And then the restrictions become really more complicated as you have higher order autoregressive models. So what you really need to know is that most softwares can take care of this very well. Next, we talk about moving average models. Moving average models have a completely different type of representation, where MA models are written as a time series expressed as the sum of past innovations. So you have YT equals some constant plus your white noise error. These are all white noise errors, just that you have a lot of lags here for white noise errors. You have a multiple regression with past errors as predictors or regressors. Okay. Now, this type of a representation is an MAQ representation, which is to say that this is a model which is a moving average process of order Q. Q represents the lags, the number of lags that epsilon would have, or the highest number. So you may have lag 2 or lag 3 missing, but as long as you have the qth lag, the process is going to be called MA, our moving average process of order Q. Epsilons are also referred to as shocks or innovations, and I have given you some context about this earlier. Now, here is a representation of what an MA1 process looks like and an MA2 process. Okay, it makes no sense unless you try to simulate this on your own, which you can do, and I've provided the code for that. Here you have YT equals 20 plus epsilon t plus 0.8 times epsilon t minus 1. Again, the time series length is 100. This is what the process looks like. What you're doing here is essentially, again, generating random normal errors and simulating the true process. And mind you, these are pure time series. These are simulations. These are not, we're not doing guesswork on some kind of data and saying, well, this is the process that governs the data. We are actually simulating in this case. So the autocorrelation functions or the partial autocorrelation functions are going to be for a pure process. Here's an MA2 model, and you can simulate many, many different types of models. Now, the important thing to remember is that we can go from an MA infinity or MA infinite representation to an AR process and an AR process to an MA process. So the first thing we're going to talk about is that any stationary, remember, stationary AR process can be written as an infinite MA process. This is due to the Vol's theorem and Yule-Walker equations that we will not go into. But the idea here is if you iterate on the autoregressive process of order 1, which says yt equals phi1 yt minus 1 plus epsilon t, and you keep substituting in the values of yt minus 1, right? So yt minus 1, if you just iterate this equation one period back, you would get what this yt minus 1 is. You substitute in, then you substitute it in for yt minus 2 and substitute in for yt minus 3. You would get this process. You can iterate on it, and you would get something like this, where you can write yt as the sum of past innovations. And this is an infinite order moving average process. So in theory, we can't really, in theory, we can have an MA process of the infinite order, but in practice, we really can't deal with an MA process that has an infinite order. So we might want to, because of this equivalency, we might actually be okay if we just estimated an AR1 model. because this is something we can do. We actually do observe the data in this case. Now, there is a term called invertibility. Now, if you have an MAQ process, that can also be written as an AR infinite representation if there is some kind of restriction, or there are some kinds of restrictions that are imposed on the parameters of the MA model. In this case, if you can go from an MA model to an AR representation, the MA model is called invertible, or the property is called invertibility. And these can really help us in modeling ARIMA models. Okay, so we will not go into details about what this means and how we get to this, but in practice, we can actually use invertibility for a lot of forecasting applications. So the invertibility of an ARIMA model is equivalent to the forecastability of an exponential smoothing model. This is something to remember. This is just to see if there are exponential smoothing models that are aligned with ARIMA models. Just like we had constraints for stationarity, we also have general constraints or conditions for invertibility. Again, the complex roots of this characteristic equation from the MA model should lie outside the unit circle on a complex plane, and this would translate into the value theta, which is the parameter that you have in your MA model. If you had an MA1 model, the absolute value should be less than 1. What this does is that it ensures that more recent observations get more weight than those from the distant past. Okay, very similar to what we were doing in the AR representation. So we're not giving equal weight to the lagged values, but we are giving more weight to recent observations and less weight to those from the distant past. Okay, and then more complicated conditions apply for higher order MA models. Finally, we can write down our autoregressive moving average model. We will ignore the I term for now. This is just the order of integration, but an autoregressive moving average model can be written as the sum of the autoregressive component and the moving average component. Okay, so the first line here is your autoregressive component, the last line here is your moving average representation, and you have your white noise error. So predictors or regressors include both lagged values of y and lagged errors. There are going to be conditions when you are estimating ARIMA models. Conditions are going to be on ensuring stationarity and also on ensuring invertibility. Now, when we talk about autoregressive integrated moving average models, which is really our ARIMA models, what we're doing is we're combining the ARIMA model with the concept of differencing. So remember, in the first couple of videos for this chapter, we talked about going from a non-stationary process to a stationary process. And in doing so, we use what is called differencing. Whether we use seasonal differencing or we use first order or second order or higher order differencing, that's up to us to know when does the time series become stationary. So the order of integration in ARIMA models is going to be equal to the number of times you have to difference the time series. Okay, so your lag operator or your backshift operation to the dth power or the dth order would allow you to estimate an ARIMA model after the time series is made stationary. So to write it out, we have three components to the autoregressive integrated moving average model. First is the autoregressive representation, which is of the pth order. For the autoregressive part, this represents how many lag values of y do you have, and that's p. The next thing is the degree of first differencing that is involved for the process, which is d. if you have to difference the series, let's say it was Google stock prices, if you had to difference it once to make it stationary, then D equals 1, and the order of integration is 1. And so that's the degree of first differencing involved. And the last component of the ARIMA model is the moving average part, which is represented by MAQ. So Q is the order of the moving average part. Now there are a few representations that make sense. So if you have a white noise model, then of course you don't have any degree of dependence, time dependence in the data, or linear time dependence in the data, and your ARIMA model can be represented as ARIMA 000, which is saying that your AR component has 0 lags of Y, your order of integration is 0, or the degree of differencing that is involved to make the time series stationary is 0, and finally that there are no lags for the error that's in the model. So that's also 0. So white noise model is ARIMA 000. And you can change this up. Once you know what a white noise model looks like, then you have different models that can be represented. So you have a random walk model here, which is an ARIMA 010 with no constant. You have a random walk with drift, which is an ARIMA model 010 with constant. This basically means that a random walk model with or without drift has to be differenced one time in both cases here to make it stationary. Okay, and finally you have your ARP representation, which is just ARIMA P00, which is a standard autoregressive process of order P, and finally an MAQ model, which is ARIMA 00Q, which is representing the qth order for the MA process. So once we have the ARMA model written out, it's usually easy to combine these different components of the ARMA models to form more complicated models and work with backshift notation. We won't get into the details, but here what you have is an ARMA model. But if you were to write out the simplest of the ARIMA models, not the simplest, but one of the simple ARIMA models, which is ARIMA 111, you would have the representation as follows, where you have the AR component, which is represented by the backshift notation. In this case, it's not 1 minus B, but 1 minus phi1 times B, where you have the persistence. So this is the AR1 component. 1 because B is to the power of 1, and then the first difference, which is the number of times you need to difference the time series to make it stationary. So in this case, it's just 1 time because this is 1. And then finally, the MA1 component on the right side. So if you open this up, you would get the ARIMA 111 representation. If you like this format, you can write it this way, or if you like it written out completely so you can see the different components, then it is just going to be YT equals C plus YT minus 1 plus phi1 times YT minus 1 minus phi1 times YT minus 2 plus phi1 epsilon T minus 1 plus epsilon T. Okay, and if you're wondering why do we have different lags here, this is because we are actually integrating the time series. We are taking the first differences of the time series that results in more lags being represented in this equation. Now there are different forms of representing these models. This is getting more into theory. What you need to remember is that R uses the mean form and the package Fable uses the intercept form. That means that it would demean the data when trying to take the difference. Okay, so here you can see that in the mean form you're trying to demean the data before you take the difference, versus in the intercept form you actually have the first difference, but you also have a constant term that is represented.